SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering, and today we shall discuss about the first and second laws, to be precise the combined first and second laws applied to different non-flow and flow processes. You know that in the last class we have discussed about the mathematical formulation of the combined first and second laws. We also could derive the expression which is obtained by making use of second law and the property relations. And we also have discussed about one particular process, that is the reversible process, that is reversible constant volume process. So, just for brief recapitulation what we have done today, if we write that this is combined first and second laws. So, basically you know that we are trying to again just write the mathematical formulation of the combined first and second laws essentially for a system, and that system is a control mass system. So, if the system is a control mass system, and if we can write it, and assuming that the processes are occurring within the system are the reversible processes. So, if we write that, we could write first law del q equal to du plus delta w, and from second law we could write delta q by t via reversible path. In fact, so long we are using this equality sign, it is valid for the reversible processes. So, if we try to write these two, if we try to combine these two laws, we will be getting T ds is equal to, that is du plus delta w, and if the system contains a substance, and if the substance is a simple compressible pure substance, then the work done can be written in the form of PdV. So, that is what we could write, this is du plus PdV. You know that this equation is again we could write taking one important assumption. What is that? We have ignored the changes in kinetic and potential energies. So, basically if the system is changing its state from state 1 to state 2, the changes in kinetic and potential energies are ignored, and pertaining to that case combined first and second law takes this form. Ideally it should have been greater equal. So, this inequality sign is valid if the process is a reversible process. Now, question is, if we use the just second law and property relation, that means del cube is less equal to TdS, and this is du plus PdV. So, this is basically obtained by making use of second law and property relation. So, this is first TDS equation I have used. You can recall that if we do not use this inequality sign, the first equation and the second equation are, these two equations are similar. So, these two equations are similar provided if we remove this inequality sign from the second equation. Okay. So, you know that we also have discussed in the last class if the process is a reversible constant volume process, right. So, if the process is reversible constant volume process, just for the recapitulations, what first law we can write. So, that is a reversible constant volume process. Okay. So, first law you know that we can write del q equal to du. In the specific form we can write del q equal to du. You know that if we try to integrate this equation from process 1 to 2, because this is exact differential. So, we can write 1 to 2, that is 1 to 2, that is u 2 minus u 1. So, the amount of heat exchange because of the change of state from state 1 to state 2 performed by the system is nothing but the change in internal energies. So, basically constant volume process, though this work done is 0. And what about second law? Second law, that is reversible process. So, basically we do not consider this inequality sign. So, that is del cube. So, this is basically again delta W plus du. Just if we use the first law, maybe this fellow equal to 0 for this particular case, and if we write the property relation TdS equal to du plus PdV, but this PdV equal to 0. So, plus PdV. So, constant volume process. So, this fellow again equal to 0. So, what we can see is, so this is property relation. Right. So, this is the property relation. So, what we can write is that this equation. So, if we now look at these two equations, say if this equation is 3, this is 4, this is 5. So, apparently we can see that equation 3, equation 4 and equation 5, these 3 are 3 different equations. But if we look at carefully that these 3 equations are not 3 different equations, rather these are the 2 equations, because equation 4 and 5 they are identical. So, it is very important, to discuss this particular aspect, I have again discussed this particular process today. So, so long as the process is reversible, the property relation is not an additional equation to describe this particular process. That means, the combined first and second law for a reversible process is exactly equal to the property relation. So, it is obtained. So, the property relation that we can see from equation 5, it is obtained by combining first and second laws specific to the case of a reversible process. So, it is not an additional equation. It would be an additional equation if the process is not reversible. So, you should keep in mind that. Okay. So, again I am telling, so long as the process is reversible, equation 5, that is the property relation, is not an additional equation. So, this is just the derived equation obtained by combining first and second law. Remember that the combination of first and second law specific to the case of a reversible process. Typical example, that can you tell me what is the example of this constant volume process? You have studied in that thermodynamics. Say if you have a container and this container is having these two stops and on the top there is a piston. So, piston is at rest on the stops initially and this container is having one pure substance, say water. If we keep on supplying heat from the bottom of the container, piston will not start moving towards top until and unless the internal pressure overcomes the pressure due to that is the atmospheric pressure plus the weight of the piston. So, basically that atmospheric pressure is acting. So, force due to that atmospheric pressure plus the weight. So, these two should be balanced by the internal pressure. If we further supply heat and if the internal pressure increases further, the piston will start moving upward. So, basically until that moment this is a constant volume process, because that the volume of a water is remaining constant. Until and unless piston is moving towards the top, the volume of the pure substance, that is water, will remain constant. So, that is a constant volume process. Okay. So, today again just I wanted to recap this. So, next we will be discussing about reversible constant pressure process. So, this is reversible constant pressure process. Our objective is to frame the mathematical equation of the combined first and second laws along with the property relation. Why we are doing so? As we have discussed in the last class, that our objective is to find out the efficiency of a system in which there are different processes. So, there could be several processes, maybe one process is reversible constant pressure process. If we know, so first of all we need to identify what are the properties we know at the initial and final states and which property we are really looking for. So, basically if such a process is there in the system, that is reversible constant pressure process, then what would be the first law, second law, combined first and second law and the property relation. So, first law, constant pressure process. So, first law would be del cube equal to du plus del w, right. So, what is work done? That is very important. Pressure is constant. Again, we are assuming that the system is containing a substance which is simple compressible pure substance, right. So, the changes in pressure, volume, temperature are considered. Other effects arising out of the electrical magnetic forces are not considered. So, basically that here delta W equal to P dV. So, that P is constant. So, basically if we try to integrate it to obtain the work done, so we really do not know whether pressure and volume, the change in pressure volume following the path. So, basically system is changing its state from 1 to 2 following a particular path. If we really do not know, because delta W is the path function, so it is like this. So, basically we need to know the relationship of pressure and volume of that, how it changes following that particular path. So, this is 1 to 2 P dV. You know that since P is constant pressure process, pressure does not change in the process. So, you can take it out. So, basically it is P dV, or you can take it you can take P outside. So, that is V 2 minus V 1. So, this is first law. What about second law? Second law is a reversible process. So, T ds equal to del cube, right. So, this is the second law. Now, I mean this is very important that this is because we are not using inequality sign, the process is reversible process, and what we can do. So, basically we can write that ds equal to del cube by T, we can write specific form del cube by T. So, if we integrate from 1 to 2, we can write S 2 minus S 1 change in entropy is nothing but 1 to 2 del cube by T. So, if we erase it, so this is small cube. Okay. This is the equation. Now, I have something to say here, that, so this is P dV, right. So, this equation we can write like this. So, del cube equal to del u plus delta w, small w, and du plus this is P dV. So, it should be small volume because we are trying to write in specific, we are trying to write all quantities in specific form. So, this is P dV. Since pressure is constant, very simple that we can write del cube equal to d of u plus P v. We can write it because pressure is constant. So, this is as good as du plus P dV. So, what is this? You have studied in thermodynamics. So, this is again one derived property, that is enthalpy. So, this is small h. So, the first law takes a form like this, that del cube equal to du plus dh. So, this is the first law for this particular process. So, this is first law of thermodynamics for this particular process. Try to remember it, that we shall be using, rather I shall tell you at this point that we shall be using these expressions frequently when we will be discussing about several thermal systems. So, if this is the first law of thermodynamics for a reversible constant pressure process, and you can see that del q equal to dh. So, we can write one step further, that is 1 to 2 dh by t. Okay. So, this is basically first and second law. Now, very important that I would like to discuss all these just from the graphical representation along with one practical example. So, what would be practical example? That you are supplying, if we go back to the previous one, say you are having water in a container. So, instead of having, now what is happening, you are supplying heat. Time will come when internal pressure will overcome the pressure due to atmospheric pressure plus weight of the piston, and piston will slowly move up, and the process is that time is known as constant pressure process. So, try to understand until piston, there will be a moment when piston will start moving upward, until that moment process is constant volume process. When piston is moving towards the top, essentially following this force balance, that is internal pressure is higher than the pressure due to the weight, the internal pressure is greater than the atmospheric pressure which is acting on the top of the piston plus weight of the piston. And if we continue supplying heat to the system, maybe piston will slowly move up, and maybe we are allowing that the supply of heat will be continued until, so when piston is moving up, the volume of water will, not water, maybe it will be converted to steam, depending on the temperature. So, the volume of the substance will keep on increasing. So, it is no longer a constant volume process, rather constant pressure process, because the process is executed in presence of the atmospheric pressure. So, you know, when this upon receiving heat, this volume of the substance is getting increased, you can see the piston is moving up, but it is moving up against the atmospheric pressure. So, this is a constant pressure process. So, this is a constant pressure process, and I am telling that supply of heat is continued until the volume becomes double. So, initially volume is this, and if it volume is double. If that is the case, so this is an example that is reversible constant pressure process. Why you are telling reversible? Because movement of piston is very slow, quasi-statically. So, you know that the work focuses on the system boundary, I mean on the here is the reverse, that is PDV type of work. So, the movement of piston is very quasi static. So, the deviation from equilibrium is almost nil. In that case, we can express the process by a reversible constant pressure process, and for which we have derived the expression. So, let us now try to map the processes in thermodynamic planes. So, this is P and this is V. Okay. So, you know, constant pressure process. So, this is P equal to P1. So, if the constant pressure process, what I said, say initially water temperature is somehow here. So, when piston is about to leave from the top of this stops, that time some amount of water has converted into steam, and this is two phase mixture, and we can represent that particular point, say here. So, this is 1, and now what I said that if this is the corresponding volume, so this is V1. What I said that heating is continued until volume becomes double of the initial volume. So, you know, so this is so basically process will continue. So, V1, that is 2 V1, say here. So, here, so this is the final point. So, this is 2. So, this is V2. Okay. So, this is what I was discussing, that heating is continued until volume is doubled. So, basically this is V2 is equal to 2 V1. So, that is the process. So, this is basically work done, right. So, that is work done during the process. Similarly, if we try to represent the process in the TS plane, why you are trying to map the process in TS plane, you have studied in thermodynamics that the area under this process line in PV plane will give you the work done during the process. Similarly, if we can map the process in TS plane, and then area under the process line will give us the quantification about the heat which is added to the system. Again I am coming back to the previous slide. Upon receiving heat, so this is heat. So, upon receiving heat, substance phase will change. Now, to have an estimate about the heat which is being added to the system for this particular case, that until volume of the substance is doubled, we can map the process in TS plane. So, you know that this is the TS plane. So, you know that pressure is remaining constant. So, constant pressure line, but temperature changes. So, you know that definitely temperature has to be changed, volume is also getting changed, pressure is remaining constant. So, you know that temperature is getting changed. So, this is T1. So, this is T1. So long as the process is, the process line is within this vapor dome, pressure and temperature are correlated. So, basically if pressure is remaining constant, temperature also will remain constant. So, this is T1, maybe we are, I mean the heating is continued until the temperature becomes T2. So, this T2 is greater than T1. So, say this is 0.2 and this is 0.1. So, you know that if we try to so this is heat transfer. Okay. So, this is the amount of heat which is added to the system. Okay. So, you know that this is the line. Okay. So, you know we have discussed second equation. So, we have discussed about constant volume process, we have discussed about the constant pressure process, and all these processes are reversible. Mind it, in reality it is very difficult to have or achieve a process to be reversible. So, all processes are irreversible process, but why we are doing so? Essentially we are trying to discuss about reversible process towards the quantification of the work which is being added to the system and heat which is being heat which is being added to the system and work which is done by the system. Okay. So, next we will be discuss about reversible isothermal process. So, then reversible isothermal process. So, the combined first and second law we need to write for the reversible isothermal process. You can understand that reversible isothermal process is temperature is remaining constant. So, you know that TdS equal to del cube equal to del U, we are writing in not the specific form. So, we are writing du plus delta W, right. So, this is what we can write. Now, temperature is remaining constant because process is reversible isothermal process. So, we can write, we can, if we integrate it. So, basically this is, or we can write TdS in specific form del cube equal to del U plus delta W. So, just if we integrate, I mean say process, the system is changing its state from 1 to 2 for this particular process. So, we can write T into S2 minus S1 equal to 1 to 2 del cube equal to U2 minus U1 plus 1 to 2 del W. So, this is not capital W. So, this is small w, not specific. So, this is what is the expression. So, again we need to map the processes in TV and PV plane. So, what could be the example? Example is say again we can take the same example that steam. If we compressed the steam reversibly and isothermally, right. So, for example, I am writing example steam is again a pure substance, is steam water mixture also is compressed reversibly and isothermally. If we compress steam reversibly and isothermally, say to a particular specific volume. So, what is the meaning of this particular process? We would like to compress or reduce the specific volume. So, if we would like to reduce the specific volume, we need to have this particular process, that reversible isothermal process. I mean, we are compressing steam reversibly and adiabatically. So, can we represent these two processes in TV and PV plane? So, you know that I am trying to write here. So, this is V and this is P, right. Isothermally, so basically you know the constant temperature line okay. So, you know that it is compressed, so definitely pressure will reduce. Okay. So, if the pressure is reducing, say we are having somehow here and it is reduced up to this particular point. So, this is P1 and this is P2. So, I am removing this. So, you know this is P2. Okay. So, now this is the work done. So, this is T equal to T1. Temperature is constant. So, process is isothermal process, but we are compressing. If we compress it, you know, or you know that say we are compressing, so this is the work done, right. So, this is very important that you know, if you would like to compress, pressure will increase. So, suppose this is 0.1, this is 0.2 and the process is along the constant temperature line. So, this is the process, right, 1 to 2. So, this is the work done. So, basically you know that we need to increase the pressure, you have to compress it, pressure will increase, and our objective is to reduce the specific volume. You can see that the volume is getting reduced from 1 to 2. So, objective is steam is compressed reversibly and isothermally to reduce the specific volume. So, you know that it is specific volume. So, this is the work done. So, work done needed for this particular process is nothing but the area under this process line. If you would like to have the corresponding TS diagram, so this is T, this is S, right. So, you can understand temperature is remaining constant and temperature is remaining constant. So, say this is a constant pressure line, this is another constant pressure line, right. So, objective is to increase the pressure or reduce the specific volume, but temperature is remaining constant. So, I can erase it, I can erase it, I can erase it. So, this is say constant pressure line and temperature is remaining constant. So, say this is, let me, so this is the case. So, for this T equal to constant. Now, say this is constant pressure line, a constant temperature line. If that is the constant temperature line, then you know this is another pressure line. So, this is P equal to P1 and this is P equal to P2, and So, again I have to erase it because of the space issue, okay. And what I can do, I can, this is S, so this is suppose it is coming up to this point, right. So, this is basically the heat transfer. So, try to understand, this is point 1 and this is point 2, constant temperature, because point 1 and point 2, these 2 points lie on the same temperature line, constant isothermal process, but what you can do, you can reduce the specific volume and pressure is increasing from P equal to P1 to P equal to P2. So, this P equal to P1 and P equal to P2, these two are the constant pressure lines, right. So, this is constant pressure line. So, you know that this is P equal to P1. So, these two are the constant pressure line, while it is compressed, steam is compressed reversibly isothermally, temperature is remaining constant, specific volume drops. So, this is the amount of heat transfer. Okay. So, what we are, what we can see from this, that if we can identify the process, we can map the process in PV and TS plane. From there we can quantify just by knowing the process line, the work being done by the system or heat which is added to the system. Okay. So, this is the constant volume process. Next one is reversible adiabatic process. Reversible adiabatic process. You can understand, the name is implying that the process is reversible adiabatic process. So, for the reversible adiabatic process, you know that if you expand steam, you have seen that expansion of steam in the turbine. So, example is expansion of steam in steam turbine. Just for for the sake of completeness, what is done in using a turbine? In turbine, steam is allowed to flow through the turbine. Steam is produced in boiler and that steam is taken to the turbine, definitely not directly, but steam is allowed to pass through flow nozzles and then only taken to turbine. Now, when steam is passing through the turbine, it does work on the rotating part of the turbine wheel, that is runner. So, if we consider that while steam is passing through the turbine, the process would be reversible and adiabatic. So, basically you know that at the inlet to the turbine, steam is having high enthalpy and that enthalpy will drop during its course of flow through the turbine, and it is because of this enthalpy drop we will be getting work output. Now, if we allow that during the flow of steam through the turbine, heat will be transferred from the system to the surroundings, maybe the work output from the turbine will be reduced. If the work output from the turbine is getting reduced, it will definitely have impact on the overall efficiency of the cycle or plant. So, this is an example. So, reversible adiabatic process. So, if the reversible adiabatic process is there, then del cube equal to 0 equal to du plus delta w, right. So, this is reversible adiabatic process. What we can see is that del u equal to minus delta w, right. So, this is the example. In a way we can write that work done. So, basically 1 to 2 delta small w equal to minus 1 to 2 du. So, basically U 1 minus U 2, right. So, this is basically U 1 minus U 2. So, try to understand that work that will be done by the steam on the rotating part of the turbine is nothing but the change in internal energy U 1 minus U 2. Okay. So, that is the case what we can see from this, and so this is from the first law, and from the second law we write that ds equal to del cube by T equal to 0, it implies that S2 equal to S1. So, this is very important. You know that frequently you have studied that reversible adiabatic process is isentropic process. So, the process will have, I mean, the entropy at the initial state and entropy at the final state of the process is remaining same, that is S2 equal to S1. So, this is constant entropy process. Okay. So, if the process is reversible adiabatic, so this is S2 equal to S1. So, can we map these two processes, I mean can we map this particular process in PV and TS plane? You know that if we try to draw it in PV plane, then what would be the process? Okay. So, this is the line, and now what we can do, say this is the point 1 and this is the point. So, this is point 1 and this is point 2. So, if we remove it, okay. So, this is point 2. So, this is P 2, okay, and this is the saturated vapor line. You know, so this is the process 1 to 2. So, this is in PV plane, and the TS plane is, so you can understand what will be work done. Again let me write it. This is point 2. So, this is work done, okay, and this is point 2. And similarly, what we can do, we can draw the process in the TS plane. So, you know that isentropic, so basically we could establish that the entropy is remaining constant, that is isentropic process. So, you know that pressure changes from P1 to P2. So, say this is P2 and another constant pressure line, this is P1. So, maybe this is the process. So, this is 1, this is 2. So, this is 1, this is 2. So, this is isentropic lines because S2 equal to S1. Okay. So, this is S2 equal to S1 and this is constant entropy line. So, what is heat transfer? So, you know that this area under the process line in this particular case is 0. So, this is no heat transfer. So, basically we can write del Q equal to 0. Okay. So, this is basically what is a reversible adiabatic processes. So, we have discussed about 4 different processes, that is reversible constant volume process, reversible constant pressure process, reversible isothermal process and reversible adiabatic process. We have taken 4 different examples to illustrate these 4 different processes. So, now what we will be doing, because you know that we have discussed about till now for the in all these processes, I mean considering the combined first and second law and second laws and also the property relation. So, today we will discuss about one important thing, that is, you know, that work done. So, basically, you know, which is very important. So, we have seen that, you know, either work is done by the system. So, basically energy is transferred from the system by work, or energy is added to the system by heat. If the processes are flow processes, and if we try to find out the energy addition to the system or energy, you know, rejection by the system, or energy addition to the system by heat, or energy which is taken away from the system by work, then we can write first law of thermodynamics across the control volume. So, first law of thermodynamics across the CV. If we can recall that we have discussed this particular part, we have seen that this can be written Q dot minus W dot equal to d E dt CV plus m dot E H E plus C square by 2 plus Z E G Z E minus m dot I H I plus C I square by 2 plus G Z I. You know, this equation is obtained under one important assumption, that is the properties are uniform over each flow sections. So, it is obtained that properties are uniform over each flow sections. Now, and it is because of this, so this is an assumption, and it is because of this we could take out this H E plus C square by 2 plus G Z E outside the integral when it is obtained from the Reynolds transport theorem. So, this is basically, you know, that this equation, so this is the rate equation, right. We also can write, you know, in not in the rate form. So, why I am writing, we will be discussing that if we apply the steady state steady flow processes. So, for the steady state steady flow processes, steady state steady flow processes. So, basically if I take the first letter SSSF, then we will be getting this for the steady state steady flow processes, and if we do not write this in the rate form, that is if we integrate it over time over the cycle, then we can write del cube equal to, you know, delta W plus m E H E plus C square by 2 plus G Z D minus m I H I plus C I square by 2 plus G Z I. So, you know that this is the equation. I mean, if we integrate this equation over time over cycle, then we can write it. Why? For the steady state steady flow processes, this d dt is equal to 0. So, the state is steady and also there is no steady flow. So, properties does not change with time. So, density does not change with time. So, basically you know that we could write this equation only for the case that the product of mass and energy do not change with time. So, this is the steady state steady flow processes valid for, and we could write it that the product of mass and energy do not change with time, right. So, together with we also can write, so this is the energy balance. Now, the steady state steady flow energy balance, and also we can write mass balance, that is M E equal to M I. So, this is mass balance. I told one thing that energy balance is not a balance in an isolated manner, rather energy balance has to be coupled with the mass balance, and that is why we could write this. So, M I equal to M E. You know that we also can write this equation in other form, that is del cube minus H I C I square by 2 plus G Z I equal to delta W, this is plus H E plus C square by 2 plus G Z D. Okay. So, this is the important equation I am making. I am keeping this equation in this box. So, we will be using this equation frequently when we shall try to find out the heat and work interaction of a process occurring in a particular device, particular system. So, this is the steady state steady flow equation. So, why I am writing? Because if you would like to apply the first law or also the combined first and second law applied to the flow processes. So, this is the equation we shall be using frequently. You know that I have taken summation keeping in mind that there might be multiple exits and multiple inlets. So, here E stands for E for exit, I for inlet. Okay. So, this is very important equation we shall be using. Since we will be using frequently, so I was thinking to derive this equation, not full derivation, but from the derivation that we have done in the previous class, one of the previous classes, I have recalled that and I have written in this form. So, now as I was talking about that, maybe now we can identify if particular system, when a particular system if we considered, and if we know that the process occurring inside the system or in the system is whether an heat interacting process or work interacting process. So, by identifying that particular process, we can easily calculate the, suppose if the process is not, and suppose the process is not a heat interacting process. So, this del Q term will be equal to 0. So, in that case we can easily quantify the work done by the system by the process is nothing but this change is this. Okay. Maybe we have to take another one important assumption is that the changes in kinetic and potential energies are negligibly small, and then simply the work done by the process is nothing but the change in enthalpy. So, that particular equation, I mean this particular equation will be very much useful when we shall be trying to find out the energy interaction in a process, whether it is by heat or work, when there is a flow. So, from this equation again we shall try to, from using this equation and by considering second law of thermodynamics, we shall try to find out work done in a reversible adiabatic and work done in a reversible isothermal processes. So, work done in a reversible adiabatic and reversible isothermal processes is also an important. We shall try to derive an important equation, and we shall see that the work done by reversible isothermal process is equal to the work done in a reversible adiabatic process. This particular exercise we shall discuss in the next class. With this I stop here today. Thank you.